I have a quote for you. Let me read it for you. Listen carefully. I will ask a question to you. A good stock of examples, as large as possible, is indispensable for a thorough understanding of any concept, and when I want to learn something new, I make it my first job to build one. Paul R. Hamus. So my question is, to understand a new concept, what is the best way to understand a new concept?
Examples?
What?
Examples?
Exactly. In this video, we will see many examples of groups. Before that, I will have a concept, abelian group. After that, we will go to the examples of groups. Abelian group. A group, the set is G, operation is star, is said to be an abelian group or commutative group if it satisfies the commutative property. The commutative property. That is, for all A and B of the set G, when A is operated with the element B under the operation star, that is same as B star A. And this property is known as commutative property. If a group moreover satisfies commutative property, then the group is said to be an abelian group or commutative group. And this term is named after mathematician Abel. You perhaps know there is no Nobel Prize in the field of mathematics, and Abel Prize is considered as the equivalent to the Nobel Prize. And let us see examples now, and I will see what abelian groups and other things in the example. Let me erase it. Abelian group. And we will have a group bag here. We will have a happy little bag for you. This bag is named as group bag. Group bag. And this bag is yours. In the end of video, I will hand over this bag to you. Let us see examples. Examples of groups. We will have a set and binary operation, or simply I will write operation. Then we will see if it is satisfying all four axioms of the groups or not. First one, I will take the set of integers under addition. This is addition. Let me separate our bag from the examples. Our set is set of integers and operation is addition, ordinary addition, the integer addition we are familiar with. Let us verify if it is satisfying all group axioms or not. First one is closure. And we have for any two integers, their sum is also an integer, therefore closure property will satisfy. Next one is associativity. for any three elements A, B, C in the set of integers, A plus B plus C in bracket here is same as keeping A and adding B and C first, then with A, and this associativity property satisfied in the set of integers under the operation addition, therefore associativity holds. Next we have identity. Is there any identity in the set of integers under the operation addition? Yes, we have 0, an element of the integers, and 0 plus any element, any integer is same as A, and A plus 0 is same as A for every A in the set of integers. So we have an identity. Next, inverses for any element A, an integer, we have its negative also an integer, and this will act as the inverse of the element A, because A when added with the negative of A will have the identity, and this happens in the other way also. Therefore, the set of integers under addition satisfy all group axioms, hence it is a group. So we have in our bag the set of integers with the operation addition, a group element. Let me put it in another color, Z plus, the set of integers under addition. And similar argument also holds for the set of rational numbers under addition, set of real numbers under addition, set of complex numbers under addition. So all these are groups, and set of real numbers under addition, set of complex numbers under the complex addition, because they will satisfy all group axioms. Closure holds, associativity also holds, identity, 0 will act as identity, and inverse of every element is its negative in all these four sets with the operation addition. So this form groups, and moreover with this abelian, we'll check the commutative property, commutativity for any two integers, for all A, B in the set of integers, A plus B is same as B plus A. It does not matter in which way you are adding. So commutativity also holds, and these are abelian groups. All these four groups are abelian groups, and commutativity will hold in every group. So let me erase this example. See, you can also construct groups, take any random set, take any random binary operation on it, and so that if it is satisfying every axioms, every group axioms of the group axioms, all four group axioms, then that set under that operation is a group, and if it is failing to satisfy any of the group axiom, then it is not a group. So showing not a group, something not a group, is very easy, because we have to only figure out the axiom which is it is not satisfying. Next we will have the set. We have forgotten the set of natural numbers. Operation is same addition. Closure property will work, because take any two natural numbers, add that, and that will be also a natural number. Associativity also holds in the set of natural numbers. And what about identity? Is there any identity in the set of natural numbers? Suppose we have the element 2. 2 is a natural number. But is there any element? Is there any element of the set of natural numbers which will be added to 2 and will get back the element 2? And this element turns out to be 0 only, but 0 does not belong to the set of natural numbers. So n under the set of natural numbers under addition is not a group. The set of natural numbers under addition is not a group, because there is no identity element. Let me erase it. So let me erase it. Now a set and operation. Set of integers and the operation is subtraction. Let us see if this is forming a group or not. Closure. First one is closure. See, for any two integers a and b, we have a minus b also an integer, isn't it? Take any two integers, their subtraction is also an integer. So closure property holds. What about associativity? Does associativity hold in the set of integers under the operation of subtraction? The answer turns out to be no, because 1 minus 2 minus 3 is minus 1 minus 3, which is minus 4, but 1 minus 2 minus 3 is 1 minus, this is minus 1 and this is 2. This one equals to minus 4, this one equals to 2, therefore they are not equal, hence associativity does not hold in the set of integers under the operation subtraction. Hence the set of integers under subtraction is not a group. Not a group. Same thing holds for the set of rational numbers under the operation subtraction, real numbers under the operation subtraction, and the set of complex numbers under the operation subtraction. The associativity will not work, and you will have many examples to show it is not associative. I have taken 1, 2, 3. You can have any set of numbers. Let me erase it. So the set of integers under subtraction, rationals under subtraction, real under subtraction, complex under subtraction, they are not groups. Next we will see what about the set of natural numbers under subtraction. Set of natural numbers under subtraction. Closure property will not work. Take any two natural number, their subtraction is not always a natural number. Suppose 1, I am taking 1 minus 2, I will get minus 1, which is not a natural number. So closure property will not work here. Therefore natural numbers under subtraction is also not a group. Not a group. Now let us have the operation multiplication. Set, I will start with the set of integers. Closure. For any two integers, is their product an integer? A times B, always an integer. Take any two integers, their product is always an integer. So closure property will hold. What about associativity? Associativity also holds in the set of integers under operation multiplication. For all a, b, c belongs to the set of integers, we have a times b times c is same as a times b times b, the first. So associativity will also hold in the set of integers. What about identity? Identity. Is there any identity element? We have an integer, and 1 times any integer is a, and a times 1 is a for all a in the set of integers. So there exists an identity element which is 1. What about the inverses? Inverses. Does every element have inverse in the set of integers under operation multiplication? The answer turns out to be no, because we have 2 an integer, but there does not exist any integer a such that 2 times a is 1, because a has to be 1 over 2, and 1 over 2 is not an integer. Therefore, the inverse of 2 is not in the set, hence it is not a group. We only have inverse of 1, which is 1. Inverse of minus 1 is also minus 1. But take any other integers will not have any inverses, because their inverse is its reciprocal, and which will not be in the set of integers. So this is not a group. Now let me erase it. What about the set of rationals? Under multiplication? Set of rationals under multiplication. Will it form a group? See, closure property will work. Take any two rational number, multiply them, you will get a rational number. And associativity will also hold. Rationals under multiplication is associative. Identity, there is 1. 1 times any rational number is same rational number, and other way. What about inverses? Every rational number has inverse in the set of rationals. See, take any non-zero rational, its reciprocal will act as inverse here. Suppose I have a non-zero element, suppose 2 by 3, its reciprocal is 3 over 2, and if I will multiply them, I will get 1. So for any non-zero rational, we have inverses. So what about 0? 0 is a rational number, but 0 times any rational number can't be 1. So this is not a group, because Q, the set of rationals under multiplication, not a group, because 0 here, identity is 1, identity element is 1, and there is no element, there is no rational a such that 0 times a equals to 1. Hence the set of rationals under multiplication is not a group. And same holds for the set of reals under the operation multiplication. Set of complex number under multiplication, they will not form group, because the disturbing element is there, 0. And all the above 3 axioms will satisfy, and other all non-zero elements as inverse but 0 is the only rascal, only that who is disturbing element here and which has no inverse. Sometimes in mathematics it works if we remove the disturbing element which is making problem. So let us see if we'll remove 0 from this set, will it form a group or not. Let us remove the element 0 from the set of rationals. So now we have only the non-zero rationals. Take any non-zero rational, two non-zero rational, multiply them. Let me write it. Closure property. Closure. For all A, B belongs to non-zero rationals, their product is also a non-zero rational. We can't have 0 here because A is also non-zero, B is also non-zero. If A times B is 0, then one of them has to be 0. So closure holds associativity. Associativity will also hold associativity for all three non-zero rationals. A times B times C is same as A times B times C. So associativity holds. Identity. Identity we have one A non-zero rational and 1 times any A is equals to A times 1, and which is A, and this happens for every non-zero rational. What about inverses? For any A in the set of rationals removing 0, we have 1 over A. 1 over A, I can take 1 over A now because A is non-zero. 1 over A always exists. Belongs to the set of non-zero rationals, and 1 over A is same as A. 1 over A times A is same as A times 1 over A, which is 1. 1 is the identity element. Therefore, we have inverses of every non-zero rational, hence it is a group, and moreover, commutative. It is commutative. Group is commutative. Let me write it here. Let me read it. Please pause the video to note. Commutative. For all non-zero rationals A, we have A times B is same as abelian group also. So in this bag we have this set of non-zero rationals under the operation multiplication, and the set of non-zero reals under the operation multiplication is also a group, and we have to make this bag a bigger one. I will hand over this bag to you in the end of this video. We have this group bag, and we have set of complex numbers, non-zero complex numbers under the operation multiplication. Also an abelian group. Let me erase it. Pause the video to note. You can show all these the set of non-zero reals under multiplication, the set of non-zero complex under multiplication. You have to follow the same procedure. It's not a big deal. Now in division, suppose the set of some non-zero rationals under division, will it form a group? The answer turns out no, because associativity will not work. See, suppose we have 1 divided with 2 first, then it is divided with 3. We will get what? 1 over 2 over 3 is 1 over 6, and 1 this is 2 over 3, and we have 3 over 2. This is not equal to this one, because this is 1 over 6 and this is 3 over 2. Hence it is not associative, and same holds for this set of non-zero rationals under division, non-zero complex numbers under division, because these are also these are real numbers, these are also complex numbers, and same example will work. Not good. Not a group.